Hello once again, this is Dr. Milian-Magigad-Tamayo-Kieke, and we are down to our last lecture for Unit 1-3, Inferential Statistics. In the previous lecture, we discussed the topics that are shown here in green. First, we talked about what the p-value is, and we tried to understand better how to apply the p-value approach. And then we talked about confidence intervals, what they mean, how they are obtained. And then we talked about how to check assumptions that we make for the statistical analysis. And then we also talked about the importance of sample size choice. Okay, so for this lecture, we're going to focus on understanding and solving other hypothesis testing cases. But before we go to that, again, let's first have a review question. True or false? In hypothesis testing, the probability that the parameter will take on a value within the confidence interval is 1 minus beta. Take a few seconds. Okay, so what's the answer? That statement was actually false. Okay, what made it false is this parameter here. Okay, in hypothesis testing, the probability that the parameter will take on a value within the confidence interval is actually 1 minus alpha. And again, what is alpha and what is beta? What do they mean? So by now, you should be able to answer that with confidence. All right. So if you recall, in the first lecture video in this unit, we talked about this tree, and we discussed that there are several cases in which we can apply hypothesis testing. And we mainly talked about the case where you have two means, you're comparing two samples, okay, and you have unpaired observations. Your sigmas, your variances are your standard deviations, and of course your variances are unknown, but you can assume that the two sigmas are equal, right? Now we're going to explore the other cases, and what we're going to explore next is a case where you still have two means, you're comparing two means, you have unpaired observations, you still don't know your variances, but and your assumption, or you cannot assume that sigma 1 and sigma 2 are equal. So you have unequal variances. So the important things that you have to know are basically three things. Okay, what is your H naught and H1? Okay, what is your test statistic? Okay, and what is your critical region? And of course, you can go back to the process that we discussed in the first lecture, okay, on how to implement a proper hypothesis test. Okay, but these are basically the things that will be varying, okay, across the different cases. It's actually these two, okay. You will of course see a pattern. You can have three sets, okay. You can have a two-tailed test or a one-tailed test. For your one-tailed test, you can either have the first sample greater than the second, or the first less than the second. Okay, so let's just go back first to this case. So you have two means. We have a test of two means, and we have sigma 1 is not equal to sigma 2. So the test statistic here basically is T naught is equal to this expression. So observe, we are using the T distribution here, all right? And when we're using the T distribution, we have to find out the degrees of freedom. Okay, so for our T naught, it is equal to y1 bar minus y2 bar all over square root of s1 squared over n1 plus s2 squared over n2. Okay, and of course, our s here are the standard deviations from the sample. Okay, and this is how you compute for your degrees of freedom. Now, I will show here later on results, for examples, 4 examples that we obtain from using R. Okay, and of course you can implement this test in Excel or Minitab. But before you go to that or in the background, you have to make sure that you're able to at least apply, okay, these equations by hand. For the next example, I uploaded already the data anyway. So then you can work with the data and these equations by hand. Okay, and then after that, you can practice using R or Excel. Okay, so this will help you understand what's going on in the software that you will be using in the future. All right. Okay, so this is a test statistic, and then you have this as your critical region. And again, what is the critical region? If you have a test statistic that falls within this critical region, what does it mean? For example, our null hypothesis is mu1 equals mu2, and our alternative hypothesis is mu1 is not equal to mu2. Then you have a two-tailed hypothesis. So you have two parts of the critical region where T naught is greater than T alpha over 2 with degrees of freedom V, and then T naught is less than negative T of alpha over 2 with degrees of freedom V. Okay, so if your T naught falls within this critical region, then you reject your null hypothesis. All right? And then, of course, this corresponds to this alternative hypothesis and this alternative hypothesis. Okay, so let's look at this example. Nerve preservation. Sounds familiar? Okay, you actually worked on this as a choice question. Okay, the abbreviated version of this as a choice question already. So now let's look at the actual problem. Nerve preservation is important in surgery because accidental injury to the nerve can lead to post-surgical problems such as numbness, pain, or paralysis. Nerves are usually identified by their appearance and relationship to nearby structures or detected by local electrical stimulation, so electromyography, for example. But it is relatively easy to overlook them. An article in Nature Biotechnology entitled Fluorescent Peptides Highlight Peripheral Nerves During Surgery in Mice describes the use of fluorescently labeled peptide that binds to nerves to assist in identification. Now, table 2.3 is not shown here, but I already uploaded the data on Vlet. Okay, and you can look at that one. You can work on that one first manually, and then using the software that you might have access to. Okay, so that data table shows the normalized fluorescence after 2 hours for nerve and muscle tissue for 12 mice. Okay. So what we actually want to test here is whether the mean normalized fluorescence after 2 hours is greater for nerve tissue than for muscle tissue. Our null hypothesis here is that the mean for the normalized fluorescence after 2 hours is equal for the nerve tissue and the muscle tissue. And the alternative hypothesis is what? The mean for the nerve tissue is greater than that for the muscle tissue. Okay? So running it in R, I use t.test in R to perform the t-test. Okay? And these are the arguments. So you have x1 and x2. So this is for the nerve. This is for the data for the muscle. And then our null hypothesis, as I mentioned, is that the two means are equal. The alternative is that if you get the interpretation is actually that here. The true difference in means is greater than 0. So nerve minus muscle is greater than 0. Okay? And the variance equal? No. Okay, so that is the case that we are dealing with here. All right. So these are the results. Okay. Our computed T statistic is 2.7353. Now, go to the download the data, and then work on it by hand and see if you get the same T statistic, as well as the degrees of freedom. Okay. Now, also try to determine the critical region. Okay. And here, our computed p-value is 0.007278. Okay, actually, you can also compute for the p-value by hand. Okay. And you've done that in one of your quiz items, actually. All right, so given these results, okay, what would be your conclusion? Okay, let's first go through these questions. Is the T statistic within the critical region? Okay, without even looking at the critical region, I assume you will be able to compute that by hand, okay? Using, of course, this formula here. Oops, this one, all right? Without even looking at that, I would be able to say that, yes, the T statistic falls within the critical region. Why? Because I know the p-value. And this p-value is too low. It means that the probability that our data supports the null hypothesis. Okay, the probability that our data supports the null hypothesis is very low. Therefore, we reject the null hypothesis. Okay, and of course, we reject the null hypothesis in the case where our T statistic actually falls within the critical region. Now, second, you reject or accept the null hypothesis. I already said, I answered that. Okay, and then of course, you can also compute for your confidence interval, right? Okay. And again, I suggest that you go back to how you compute for the confidence interval and do it by hand and see if you can determine the same values. Okay. Now here are just our sample estimates. Okay, so from these results, we basically conclude that, okay, what? Since we rejected the null hypothesis, we conclude that the mean for the nerve tissue is greater than that for the muscle tissue. Okay. All right, let's move on to the next case. Okay, we have test of two means where the sigma is known. Okay, so in this case, remember we previously dealt with cases where our sigmas are unknown. Here we have sigma is known. So as you can see, the main difference is that we can now use the Z distribution, standardized normal distribution. Okay, and of course we have to adjust how we express our critical region. Okay, so these are now all in terms of Z values. Okay, we still have the same set of possible, three possible sets of H naught in each one. Okay, so take note, we now use our population standard deviation. Okay, in the T distributions, we use the sample standard deviation. All right, so you can just, of course, apply those formulas given the appropriate situation. Now, we've covered this, two means, and paired observations. Let's now move on to the case where we are dealing with only a single mean, okay? And you also have a known sigma. So in this case, again, we use the standardized normal distribution. Okay, and our t-statistic is simply the mean of the sample minus mu naught, okay, divided by sigma, the population standard deviation, divided by square root of n, your sample size. Okay, and these are the corresponding critical regions for the three sets of H naught and H1. All right, so let's look at this example on textile strength. A supplier submits lots of fabrics to a textile manufacturer. The customer would accept the lot if the textile breaking strength exceeds 200 psi. From previous experience, a reasonable value for the variance of the breaking strength is 100 psi squared. 4 specimens are randomly selected, and the average strength observed is 214 psi. What would be your recommendation? Okay, so you actually have the values that you will need to use in conjunction with the formula that I showed earlier. Okay, so what is the parameter of interest here? Second, what are your H naught and H1? Third is the t-statistic within the critical region. Fourth, do you reject or accept the H naught? And fifth, should the customer accept the lot? Okay, so let's see. What is the parameter of interest? We are interested in the mean textile strength, right? Okay, what would be your H naught and H1? Your H naught is that your mean textile strength is equal to what? 200 psi, right? Okay, and so your H1 is what? The customer would accept the lot if the textile breaking strength exceeds 200. All right. So your alternative is actually mu is greater than 200. Okay, because that's the case where you want to accept the lot, right? So what do you desire here? You actually want to reject the null hypothesis. Okay. Now, is the t-statistic within the critical region? Okay, let's see. So here, basically, we just used R to compute for the z-statistic. I just used the formula that I showed you in the previous slide. Okay, I also computed for the critical region, where I just used the Q norm function in R, okay, at 0.95. And then, okay, why did I use this, 0.95? Because if you recall, okay, we want to have z naught greater than z of alpha over 2, okay? And our, oh, this should be alpha. This should be alpha, guys. Z of alpha, negative z of alpha, right? So that's why I use 0.95 there. All right. All right. So, and then we compute for the p-value to be equal to 1 minus p norm of z, okay? So this is 1 minus the cumulative probability of z, okay, that we compute from here. And that would be our p-value. Okay, so z, our test statistic is 2.8. Our critical region is 1.644854. Okay, so then our critical region is P naught greater than 1.644. Okay, so if you just base it from here, from these two values, what would your conclusion be?
accept or reject. So it's 2.8. So hard. 2.8 is okay. So just basing from on 2.8 and 1.644, 854 here, your test statistic and your critical region. What would your conclusion be? Your Z statistic here, your test statistic is within the critical region, right? Because it's greater than 1.644,854. Therefore, you reject the null hypothesis. Okay? And of course, that would be consistent with what you can conclude from your p-value. Your p-value is too low, 0.002555513, right? Okay, and based on this, okay, if your acceptance level, for example, is if you want to accept it at 5%, then you would decide to reject the null hypothesis. Again, because the probability that our data manifests the trueness of the null hypothesis is too low. Okay? So now what I want you to do is do a little exercise, okay, on this example, burning rate. Aircrew escape systems are powered by a solid propellant. The burning rate of this propellant is an important product characteristic. Specifications require that the mean burning rate must be 50 centimeters per second. We know that the standard deviation of burning rate is sigma equals 2 centimeters per second. The experimenter decides to specify a type 1 error probability or significance level of alpha equals 0.05 and selects a random sample of n equals 25 and obtains a sample average burning rate of x bar equals 51.3 centimeters per second. What conclusions should be drawn? Okay, so I want you to do this by hand, okay? And as your attendance or participation in this activity, you should upload a scanned copy of your solution to this exercise on Ooblet. Okay. So now let's move on to other cases. So let's move on to this branch here where you have your sigma is unknown. Okay, so there could be two cases. Your sample size is greater than or equal to 30, or your sample size is less than 30. In the case where your sample size is greater than 30, as you can see, we use our standardized normal distribution. Okay, again, errata, this should be alpha. This should be alpha, not alpha over 2. You use that when you are dealing with a two-sided test, right? So this is your test statistic. Again, your sigma is, oh, what did I do here? So this should be S, not sigma, okay? So this should be S. Okay, S over square root of n. Sigma bar, X bar minus mu naught all over S over square root of n. That is your Z statistic. And this should be alpha. Alpha. Right? So that's done. And then the next case is when your n is less than 30. So as you can see, we now use the t distribution. Okay? And again, there's an error here. This should be alpha. And this should also be alpha. All right? Because we're dealing with a one-sided test. Okay, and as you can see, we use our sample standard deviation because our sigma is unknown, right? So x bar minus mu naught all over f over square root of n. Okay, and this is the different things that you have to know for the different cases are actually summarized here in this table, which is also provided in Design and Analysis of Experiment by Montgomery. You have here the different hypotheses. You have the test statistic. Okay. You have the critical regions. Okay, for fixed significance level. All right. And of course, you have the formula for determining your p-value. All right. So, so this is for the case where you have tests on means with variance are known. So that's why you can see all your signals there. And again, as I emphasized earlier, for the one-tailed test, please take note of the error in the presentation. You have to use alpha here. Okay, you only use alpha over 2 for the two-sided test. All right. So of course, this is a different expression. You can just get the absolute value of your test statistic, and it should be greater than this alpha over 2. All right. So for tests on means of normal distribution, where the variance is unknown. Okay. So then, as you can see here, we use the t-distribution, right? Okay. Now, this is the case for sigma 1 is equal to sigma 2. And then, of course, when you have unknown variance and you cannot assume that they are equal, okay, then you use this. Okay? And take note that you have your degrees of freedom. You have to know your degrees of freedom. Okay, and of course, in the third column, you have your critical region, and then you have the computation of your p-value on the last column. Okay, so let's look at an example here. Suppose that you have a hardness testing machine. This machine helps determine the hardness of, say, a metal specimen by pressing a rod, okay, with a pointed tip, I should say, shown here as the indentor, into the specimen with a known force. Okay, the hardness of the specimen is determined by measuring the indentation caused by the tip. Now, suppose that this machine has two available tips, and you want to verify whether the two tips produce the same hardness reading. How would you conduct the experiment? We can become more precise in comparative experiments when we make comparisons within matched pairs of experimental materials, actually. So here we can have randomly selected specimens, say 20, okay? And then half are tested using one tip and the other half are tested using the other tip. And then we would randomly assign the specimens and use t-test to compare means. What problems can you encounter in this? The problem, okay, in this setup where you have a completely randomized design, okay, and you can use t-test, for example, because you have less than 30 and you don't know the population variance, okay. Some problems can arise though, okay, because what if the metal specimens are in some ways heterogeneous that affect material hardness, okay? So for example, stocks were produced in different heat levels. This inherent variability of the specimen may distort the measured hardness and could therefore inflate the experimental error, making it harder to detect the true difference between the two indenters. So alternatively, we can have an experiment wherein we take measurements in pairs. So you have one bar or rod, okay, and you actually make the indentation, okay, from the two different tips on the same bar. Okay. So again, how do we do pairing or paired testing? Okay. In this case, uh, let's have the metal specimens large enough to accommodate two indentations, one each from the two indenters. Now, to have 20 observations, we have 10 specimens for which we randomly assign each indenter or tip to one half of each specimen. So suppose that we obtain the following hardness measurements for our experiment. All right. So this would be say this is what the data that we obtain. Again, the data table is already uploaded on. So I show here the statistical model for our data. Okay. So you have here the hardness for tip I on specimen J, denoted by Y sub ij. And then you have the true mean hardness of the tip, mu sub I, plus the effect on the hardness due to the specimen, okay, specimen J, denoted as beta sub J, plus the random error. And of course, again, we assume that our random error is normally distributed with mean 0 and variance of sigma sub j squared. And we have I equals 1 to 2, j equals 1 to 10 for our example. Now, if we compute the paired difference, v sub j, which is y sub 1j minus y sub 2j from j equals 1 to 10, the expected value or long run average of this difference can be derived as shown. As you can see, the expected value of the difference is equal to the difference of the expected values of the two means. This means that we can make inferences about the two means, mu1 and mu2, by making inferences about the mean difference, mu sub d. Okay, because mu sub d, okay, is actually an unbiased estimator of mu1 minus mu2. Okay, and again, these are the three main things that we've always looked into, okay, in the different cases that we've dealt with. Okay, so you have your pairs of H0 and H1, okay, and then you have your test statistic and you have your critical region. So your test statistic here is equal to the mean difference divided by the standard deviation of the difference over square root of n. Okay, and you know that the mean of t is just equal to this expression here. These are the corresponding critical regions. Again, this should be alpha. This should be alpha. Okay. So homework. Perform the paired t-test for the hardness test example in R. Okay. Upload a PDF file containing your code and results on Oobledo. Okay. What can you conclude given your results? And then read more on the advantages of paired comparison design and how it is related to blocking. Now let's move on to the test on two variances. Making inferences on the variability in data or comparing variability in data is the goal, okay, in the test on two variances. Okay. And this can be in the form of a test on single variance or test on two variances. And again, this is from Montgomery. Okay. Again, you have the different hypothesis tests with the corresponding null hypothesis and alternative hypothesis here, and the corresponding test statistic. Okay, so here, as you can see, we're now making use of other distributions. We have the chi-square distribution. If you remember from our previous lectures, I mentioned these distributions because, as I've mentioned before, these are going to be relevant, important distributions in future statistical analysis, and now they are appearing. So we've already dealt with the t distribution, we've dealt with the z distribution, now we have the chi-squared and the f distribution. Okay, so for this is our t statistic. Okay, when, for example, our hypothesis sigma squared is equal to sigma naught squared. So here we are looking at a test of a single variance. Okay, and we're comparing that variance to a specific value. Okay, in this case, we use the chi-squared distribution for the test statistic. Okay, so chi-squared is equal to chi-squared naught is equal to quantity n minus 1 times the standard, the variance of the samples all over the sigma naught squared. Okay. Oops. And these are our critical regions. Okay. This is how we compute for the critical region. Right. Now, if we are comparing two variances, okay, two samples, okay, and we're comparing the variability of those two samples, we could have, for example, h naught is sigma 1 squared is equal to sigma 2 squared. And of course, we can have three different alternative hypotheses here. Okay. And then for each case, we have the F statistic as shown. Okay. So you can see for this case, you have S1 squared over S2 squared. For the case where you're testing whether sigma 1 squared is less than sigma 2 squared, your numerator is actually S2. For the case where sigma 1 is greater than sigma 2 squared, your numerator is S1. Okay? And of course, you might be wondering, so what's the difference between these two? The difference lies in the critical region. Okay? Kasi this one is one-sided, this one is two-sided. And for the two-sided test, you have this as your critical region, and then you have this for your one-sided test. All right, so let's look at an example here. Variability of test equipment results. A chemical engineer is investigating the inherent variability of two types of test equipment that can be used to monitor the output of a production process. He suspects that the old equipment, type 1, has a larger variance than the new one. Thus, he wishes to test the hypothesis H naught, where sigma 1 squared is equal to sigma 2 squared, and the alternative hypothesis is sigma 1 squared is greater than sigma 2 squared. So sigma 1 squared is the variance of the old, and sigma 2 squared is the variance of the new one. Now, two random samples of N1 equals 12 and N2 equals 10 observations are taken. And the sample variances are S1 squared equals 14.5 and S2 squared is equal to 10.8. Okay, so given that, you can now compute for your F statistic, right? Okay, so the test statistic is S1 squared over S2 squared. Why? Because we're looking at this situation here, this case. All right, and our critical region will be this one, where these two are needed to determine your degrees of freedom. Okay, so our F statistic is 1.34. Now, from appendix table 4 of design and analysis of experiments, you will find that F of 0.05, okay, that's our alpha, and 11 and 9, okay, the value is 3.10. And our critical region is that region where F naught is greater than that value, than this value. Okay, so is that true? No. So the null hypothesis cannot be rejected. 1.34 is not greater than 3.10. Okay, which means that our test statistic does not fall within the critical region. Therefore, we cannot reject the null hypothesis. So that means we have found insufficient statistical evidence to conclude that the variance of the old equipment is greater than the variance of the new equipment. Okay? Now let's move on to test on proportions. Okay, and you can just read on this, okay, test on proportions. C. Montgomery and Runger, Applied Probability and Statistics for Engineers. There are other references. Okay, so if you will observe the pattern, there is a pattern in how to implement a test of hypothesis for different cases. You just have to know what kind of case you are dealing with. Okay, what the relevant, of course, first, what the relevant um, null and alternative hypothesis should be. Okay, and then you have to know what distribution you can assume for your parameters, and therefore what test statistic you should make, you should look at, and then find the critical region. And as I've shown you, there are tables that summarize these different kinds of these different parameters for different cases. So that is the end of our lecture. And in summary, after 3 video lectures, we were able to cover all of these topics. So we defined what hypothesis testing is, why it is important, and then we also discussed about how to implement properly a hypothesis test. Okay, so we looked at the process flow, and then we looked at a one and two-tailed hypothesis test. Okay, depending on the alternative hypothesis, and then we looked at we defined the significance level. We defined what type 1 and type 2 errors are, and then how to determine the test statistic. And as we have just discussed, there are for different cases you have a different test statistic, and of course you have your critical region, which should be consistent with the null and alternative hypothesis that you are dealing with. We defined what p-value is, and we understood its application and its interpretation. We also talked about the relationship of hypothesis testing to interval estimation, okay, your confidence interval. And then we looked at different cases, okay, for hypothesis testing. We looked at the test on single means where we could have a known sigma, sigma that is unknown, and under this case, you can either have greater than or equal to 30 or less than 30, okay? And then you have tests on two means, okay? You can have a known sigma, okay? Or you can have unknown sigma, but you can assume that sigma 1 is equal to sigma 2, okay? Or sigma 1 is not equal to sigma 2. And then, of course, you have your paired observations. We also talked about the test on single variance or on two variances. And of course, your reading assignment, test on single proportion, okay, and test on two proportions. Okay, so that's it for unit 1-3. And in the next lecture, we're going to tackle unit 1-4, single factor analysis. Basically, we're going to talk about analysis of variance. Till then, goodbye.